Yeah, I think I'm good to go.
Yeah, good to go.
All right. So my name is Alanazi. I'm actually a PhD student at King Abdullah University for Science and Technology. I'm also a reservoir engineer working for Saudi Aramco. Today, my topic is about a fundamental analysis related to a way that we would like to assess the sealing efficiency of Caprock in relation to underground hydrogen and carbon dioxide storage. And to start with, I would like to talk about the motivation, why we're after carbon dioxide sequestration and also hydrogen in particular. So over the past decade, as shown from the figures, there've been a lot of consumption of energy, which is lately being, I think, connected to the high population or the exponential increase in the high population, and which is mostly compensating from fossil fuels, and a little bit touching base on renewables. And there's a lot of studies connecting the burning of fossil fuels to the high emission of greenhouse gases, in particular to the carbon dioxide that we all pretty much know about. There are also some studies which showing that half of the annual emissions are being released to the atmosphere, and that's what caused the negative impact on the atmosphere and the whole global warming thing. And hence the governments and countries, they've get together to adopt strict environmental regulations, which include some strategies related to the decarbonization of the fossil fuels industry, in addition to the blending that with clean energy resources. And so the first initiative is to capture the carbon dioxide that we release to the atmosphere. So how about hydrogen? So hydrogen in the whole picture, or the whole initiatives, is considered as a major enabler, which related to its unique properties of storing energy, as it has a high energy density per unit mass compared to other fuels. In addition, it allows us to convert energy from renewable resources, which they suffer from their intermittent nature, and allow us to keep it for much more seasonal demands that we might need over the year. In addition, we can convert the let's say the negative fossil fuel that into more environmentally friendly form, which could come from processes like steam methane reformation, and also the gasification, which is pretty much known by blending that with CO2 to create the one type of it, which is the blue hydrogen. And that's why it takes us to the whole initiative. So we need to capture, sequester CO2. In addition, we need to store our seasonal energy into hydrogen, and the whole thing will take me to my second point. So it's been very well defined that in order to go for such diversified economy, we need to find a suitable storage medium with high capacity for accommodating all these large ambitions. So what I'm showing here in this schematic, you can see the kind of the overall picture of a diversified low carbon economy, which includes technology like geothermal technology, the renewable sources, which is the solar panels, wind turbines. So here, and it's being identified by the industry, surface facilities are pretty much very limited, and they could be hazardous, as, for example, hydrogen is very diffusive. So this is no way that we can build the whole economy based on the surface facilities. However, that takes me to the theoretical options, which is the geological formations. And in this case, we're talking about let's say, much mature option, salt caverns, and depleted hydrocarbon reservoirs, and the saline aquifers. So when you talk about CO2 underground storage, it's pretty much very well known and explored, and you can see a lot of cases in the field. And also there are a couple examples when we talk about hydrogen, but it's not specifically for hydrogen. It's hydrogen mixed with other gases. And the difference between the storage mechanisms, the hydrogen is, it's basically, the hydrogen storage is basically a cyclic process of number of cycles of injection and reproduction of the hydrogen to be used in the supply seasons, which would require an additional challenges. One of which is the requirement of a cushion gas that has to be kept inside the reservoir to keep the overall hydrostatic pressure of the reservoir not to collapse and damage the reservoir when we need to inject it back again. And that takes me to the trapping mechanisms of the gases. And the main thing that I'm presenting to you is related to the sealing efficiency. So the two major mechanisms are the stratigraphic structural entrapment. When the gas is injected, free gas released to the top of the reservoirs, which accumulate beneath the low permeable layer. We call it Caprock, and that should keep the gas, the free gas, and that mechanism per se is referred to as stratigraphic structural entrapment. And then we have the capillary residual entrapment, which is within the reservoir rocks, and for the CO2, mostly mineralogy and dissolution, which we consider to be highly more effective. And that takes me to the objective of our presentation, which is utilizing the extensive work done, or the experimental work done in the measuring wearability of a proxy of a Caprock, which is using a mica samples. It's been very well known that in the industry and in the laboratory, it could be used as a proxy for Caprock. And then the experimental work that we're utilizing, they've done a lot of they've used a lot of conditions. First of all, as an attempt to restore a more realistic, let's say, condition by introducing organic acid, and a typical organic acid that in the literature identified by its carbon atoms, and that which it could range between 2 to 26 atoms, and also we will discuss the impact in terms of sealing efficiency and also the capacity of a technique that is recommended to be used to restore the favorable wettability condition. Now, to start with, this is basically the system being used to acquire the wettability data. When we talk about the wettability, we're talking basically about the contact angle of the brine drop over the solid surface. And this work, we're using the mica sample, and then we have the brine, which is of a 10% NaCl. Now, there's two contact angle when we talk about this specific technique that is being produced by Lander in 1993, and since then been very well recognized and used by a lot of scientists. And so at this work, we produce two types of contact angle: the receding contact angle and also the advancing contact angle. The receding is more related to the sealing efficiency, structural entrapment, and the advancing is more related to the capillary residual entrapment. And basically, we apply Laplace equation, which give us an opinion about the brine resistance to the buoyancy pressure exerted by the free gas column. And as it's shown by the equation over here, it's related to the effective bore throat radius, which plays a major role in our work. And also, we calculate the maximum static column height of the free gas column. Then let me just jump to the results. So this is the contact angle data, which represents the wettability. So if we have a higher contact angle, that represents more a CO2 or a hydrogen wet condition. You can see the work presented is being done at different pressure and different temperatures. The we can just say that if we increase pressure, we will see much more, let's say, conversion of the status of our mica samples toward more CO2 with conditions or hydrogen with conditions. However, it's the other way for the temperature. So if we decrease the temperature, you will see much more impact on the contact angle toward CO2 or hydrogen with conditions. So this basically tells us that the much more favorable condition or favorable reservoirs are those with, let's say, lower pressure and much more higher in temperature. So warmer and less pressure. We calculated the equilibrium contact angle, which is very well known, and it's been used basically based on Young's equation. Merging that with Newman equation of state, we'll be able to get basically a semi-empirical correlation will help us to calculate and get an idea about the equilibrium, which is over here could be more simpler, presented by the average between the receding and advancing contact angle. One can say, we can see here from the plots between the hydrogen and CO2, the influence of pressure and also temperature are much more or less pronounced when we see the hydrogen wettability. That because the hydrogen has much more lower density than CO2, and that will also share it in terms of the capillary sealing efficiency. So these are the capillary entry pressure. So just to re-emphasize, we're talking about the brine within the Caprock, which exerts some capillary pressure against the buoyancy pressure exerted by the gas column. And you can see in the hydrogen plot, for example, we try to further assess the importance of if we have a variance on the bore throat radius. We tried 5 nanometer and 10 nanometer. These are typical values for mica bore throat. And you can see from the hydrogen that the capillary pressure get highly influenced by the change of the bore throat radius, or from 5 to 10, while in the CO2, there is actually a difference, but it's not as pronounced as the hydrogen. However, what we mean when we have a lower capillary entry pressure, that means the gas could invade and penetrate throughout the Caprock. So we don't want to go, as low as 0 or something. Now, we also try to calculate the capacity of the gas and how it could be presented within the free zone under the Caprock. You can see it's as we increase the pressure, we still have getting much more negative impact. However, for the hydrogen, it's still in the safe zone, not yet below, for example, 500 meters. But for the CO2, it's almost reaching 0, which is a little bit dangerous, because if we exceed 0, we will have a negative suction of the gas throughout our Caprock, which eventually cause the leakage of the gas crossing the Caprock into the aquifer above it. And now to the second part of it, by restoring the realistic state of our Caprock, the typical organic acids being used and aged with the mica samples for more than 7 days. And over that, we ensure that we would have an aged high TUC or high organic content sample, and we tried the different chain alkaline and also different types of acids, and then the whole process was repeated, and you can see the impact on the hydrogen and CO2. So in the plot, you can see the difference if we change the concentration of the organic acid. And this is presented by minus log, which translated to 10 to the power minus 2, for example, and 2. And at the 9, it's 10 to the power minus 9. So the concentration increased this way. And this is the highest concentration of acid that's being used and aged with the mica sample. And we try to avoid having a high value of the contacting, which means that we have pretty much very or strong CO2 wet or hydrogen wet condition, which eventually will lead out to the leakage of our gas, and we proceed to calculate the equilibrium contact angle. And then we jump to our analysis, which we would like to see would we have the sufficient capillary pressure to resist the column of the gas. And you can see over here, if we have a little bit amount of acid, that will be pretty much fine. But if we go to such as 10 to the power minus 2, that will be also dangerous, not only for CO2, also for the hydrogen escaping. And you can maybe see it better in terms of the height of the column, which could reach up highly below 500, and also a negative values that could be seen from the CO2. And this is at the lab scale, picked at and selected at specific conditions. And now to the kind of mitigation plan for restoring wettability. There are a number of methods actually to restore wettability to become more favorable, which in our case, we would like to have it more like strong water wet. And one of which is the use of nanoparticles. And because the mica has a positive charge surface, we used aluminum oxide to try to play around with the wettability and restore it back to water wet condition. And that was done basically using 10 to the power minus 2 concentration of the organic acid aged with the mica. So it's only at that high and let's say very unpleasant wet condition to just start to vary the concentration of the nanoparticles to see which one could be much more favorable concentration that could give us a conclusion. Just to comment in the influence, so nanoparticle, they help a lot to kind of decrease the wettability into more water wet. However, there is a certain concentration which the wettability could be optimally changed to and identified here using the aluminum oxide to be 0.025 weight% of the aluminum oxide, which is at the lab scale is not that much. And basically that tells that it's like one of the methods which is being recommended in the literature recently, and it could be used for CO2 and hydrogen. And this is there's a lot of discussion about this point, and now we're showing that in terms of the lab analysis. Moving forward to our capillary pressure, did it improve? Yeah, it got improved to reach values of 8 megapascal, resisting the column of the gas, and ensure that we have our gas stored under the structural entrapment of the Caprock. Finally, that's it. We've seen a decrease of the sealing efficiency with the increase in pressure, and an increase of the capacity as well, with the decrease of the temperature for both. However, hydrogen has a lower density, hence it would have, let's say, we will see less pronounced impact on when it comes to the wettability. However, the smaller the bore size is much more better for our sealing conditions, and also it will ensure that we have the capacity that we're after. And finally, we try to assess one of the techniques, which is using nanoparticles to restore the favorable wettability, and that's basically what we have demonstrated, and it would definitely improve the sealing efficiency and storage condition. Again, this is at the lab scale, and there is a lot of still ongoing, I think, investigation related to how could such techniques be upscaled to, let's say, small scale field projects. And thank you. I think I'll be ready to answer any questions.
Yeah, thank you, Amr. Very interesting presentation. Does anyone have any questions? Then I will ask the first one. So Amr, you mentioned 3 mechanisms for CO2 sequestration, and your focus in this paper is capillary, right? Capillary residual mechanism.
Capillary sealing efficiency, yes.
Yeah, capillary sealing. So my question is, what would be the approximate time domain for capillary entrapment? Do you have a number or estimate for that?
It depends, you know, like all of what I presented so far is it's a laboratory work. So it's basically using a contact angle measurement to see the impact. But again, there are actually in the literature studies showing that salt caverns are showing that the leakage, if you're talking about the time frame for the leakage throughout the caprock, yes, it could take over 30 years. And there are actually, if we talk about CO2, if you want to talk about hydrogen, there is what is called town gas. It's mostly done in Netherlands and I think in German. So they tried that. Town gas has almost 46% of hydrogen. So it's a very good example. It's being injected under salt caverns, and it has been there for more than 25 years. And they've been monitoring the leakage, and it has a caprock, which is mostly shale, of very low permeability. And I would say it depends on the caprock and the quality of the caprock.
Okay, yeah, thank you. Thank you for your answer.